So this time period between when you start the well producing and when you reach boundary dominated or pseudo-steady state behavior, there's a field of petroleum engineering that kind of is dedicated to trying to understand the well and the reservoir, all these properties, permeability and so forth, based on the study of pressures and rates during this time. Okay? And it's referred to as transient flow or rate analysis. Historically, we used to call it well test analysis. Okay? In the old days. Well testing. Okay? Where the well was produced and maybe the rates were changed over a period of days, typically. And during that period of days, they assumed that they did not reach this complete boundary-dominated pseudo-steady state behavior. So that the rates and pressures, in a sense, the behavior of the waves in the pond, if they studied those, how the wave moved out as a function of time or how big the wave, how small the wave got, I don't know, whatever. If you study the rates and pressures in this well during that time, then there was a whole science, if you will, of how to estimate the permeability of the rock, primarily. That was the main thing we're shooting for, the average permeability of the rock. And it's called well testing, and now it's called pressure transient analysis. Okay? There's a course at the department here. I think there's 2 courses, one mandatory for the reservoir group and one, I think it's an option. Is the professor there for the last 30 years teaching this course is Tom Yelmert. And when I was in college, that was kind of like the holy grail of reservoir engineering. Okay? The best of the best reservoir engineers did this, and then a few were doing reservoir simulation, but that really started a bit later. Now, in today's industry, there's fewer and fewer of these people doing well testing, pressure transient analysis, and there's more and more people doing reservoir simulation. Okay? Now, what pressure transient analysis does is that it says, it takes the differential equations describing flow, which is Darcy, which we're going to finally get to, maybe next week, but it's going to take Darcy equation and a material balance and mathematically combine the two and solve for how the pressure moves out away from the wellbore if you produce at a certain rate. And the way they do this, because it's solving a differential equation, they don't solve with all these parameters we talked about. Permeability, viscosity, compressibility, porosity, all these different variables. Because if you transform the differential equation into what's called a dimensionless form, you'll see that well A and well B could behave identically even though their permeabilities are different. Okay? Because the compressibilities are different in the other direction. Okay? And there's a term called the diffusivity constant of the rock fluid system, which is kind of fundamental to that. But the point is that we work with dimensionless pressure drop and dimensionless quantities, and we assume that the well produces at a constant rate, and we solve for how the pressure changes at the wellbore, PW. Could be PWF in reality, since we're looking at a constant rate. And we express that not as absolute pressure, but how the pressure changes from the initial pressure, the delta P. And when we solve this in a dimensionless form, meaning that we don't talk about PSI or millibar, we talk about dimensionless pressure drop, PD, and dimensionless time, TD, then that same solution can be used for all of the wells in the world. Okay? Pretty much. independent of the permeability or whatever. So we call this dimensionless pressure drop solution. PD is a function of TD. Dimensionless pressure drop as a function of dimensionless time. There's another, you can solve the same exact set of differential equations where you use the different boundary condition instead of constant rate, which is a boundary condition. You guys remember solving differential equations. You're done with that now, unless you work with Professor Yelmer. Then you have to keep doing it. The other boundary condition that can and sometimes is used is that you say that the pressure at the wellbore is constant. How does the rate change? Okay? And you get what's called a dimensionless rate solution, QD is a function of dimensionless time. Okay? And if you're a drilling engineer, or even a production engineer, and probably most of you good reservoir engineers, you'll find out that mathematically, approximately, this PD, TD, is approximately equal to 1 over QD, TD. Before boundary dominated flow. Pretty damn good assumption. Okay? It's not exact, but it's pretty close. So they're inverse functions. It's just using a different boundary condition. One, you set the rate, you get the pressure drop. The other, you set the pressure drop, you get the rate. And it ends up the solution is almost identical. It's just inverse solution. Okay? So the thing is that in reality, wells never produce at a constant rate. Okay? And they generally don't produce at a constant bottom hole flowing pressure, that there's some mix of the conditions. So in reality, PWF changes with time and rate changes with time, both. Okay? It's not good grammar. But that's the reality of what usually happens. You can still use, though, the same analytical solutions to these differential equations with changing boundary conditions. Because the differential equations are of a certain type. I don't remember what type it is, but if you have a certain type of differential equation, then you can use what's called superposition or convolution. Does anybody remember what kind of differential equation is required? I don't. Doesn't really matter, but our flow in porous media satisfies that. So that basically we can use superposition, or what's called sometimes convolution. Convolution, it's harder to spell. And that's something you'll learn about in this well testing course. Okay? It's very fundamental. Now, what is superposition or just, okay, I'll just tell you in a nutshell because I'm sure Tom won't make it quite this simple. Okay, if you got a well that's producing at rate 100 barrels a day, and then you change the rate to 200 barrels a day, okay? So what you can do is that you can say that, okay, for the first day it produces at 100 barrels per day, and for the second day it produces at 200 barrels per day, and then it just stays at 200 barrels per day for a year. Okay? What you can say is that if you put in a well from time 0 for the full year that produces at 100 barrels per day, okay? Forget the reality that the well actually started producing at 200 barrels per day after one day. You just let it produce for the whole 365 days with 100 barrels per day. And you look at what's the pressure drop due to that. Okay? Then, on your time scale starting at 0, then you go and you start a new time scale at 1 day, which is time 0, for a new well. We put another well in the same place. And we say that well is going to produce at 100 barrels per day also. But it starts a day later. Okay? And it knows nothing, the reservoir's never been touched before. Okay, so it's a fresh reservoir. Pressure initial is 0. So we put that well on at 100 barrels per day starting at the end of day 1. Then that produces 364 days. So the pressure drop at the end of 365 real days is just the sum of the pressure drop from the first well that went for 100 days for 365 days, plus the pressure drop, there's no pressure drop the first day, for the second well, and it's producing also at 100 barrels per day, but it produces for a day less, so it produces for 364. If you add the two pressure drops at the end of 365, you'll get the correct pressure drop for that well that went from 100 to 200 and stayed at 200. Okay? And if the rate changes every day, you just keep adding on a new well. What you have to do is that all the sum of all the rates of all the wells that you've got has to be the actual rate. So if at the end of the second day we shut the well in, right? You go for 100 barrels a day for a day, 200 barrels a day for another day, and then 0. The third well that starts at 2 days, what does its rate have to be? Minus 200, because we got the other two wells from 2 days on. One's doing 100 barrels a day. The second well's doing 100 barrels a day. So to cancel that out, because for the next 363 days, a long shut-in, okay? 363 days shut-in, the total rate has to be 0. And if you just take the pressure drop, delta P, from each of those 3 wells, add them together at any time from 2 days on, you'll get the right performance. Okay? That's superposition. So for the drillers, if you understood it now, you can say, oh, I understood superposition, and you don't have to worry about it anymore. Okay? But it's a very fundamental concept, and it applies basically to all of our flow problems in reservoirs. So that's this topic that we really are not going to, more than this, we're not going to come back to very much. Okay? It's this period before boundary domination starts. Okay? Now, the next thing we're going to do is that, or the next topic that we're going to cover the remainder of the semester is something that's referred to as volumetric material balance. A volumetric material balance. So what is that? It's basically a relationship that says the volumetric average pressure so you have to integrate the pressure everywhere on a volumetric basis, okay? Is going to decrease as a function primarily of how much stuff we've taken out, the cumulative amount of production, okay? And I'm going to write that as capital Q and production. So that's the cumulative volumetric production. And it's going to be either surface gas or surface oil. It might be this wet gas, but okay, it's going to be either surface. It's going to be surface volumes. Okay. What is QP? Well, QP is just the integral of the rate. Okay? And remember the rate, when we talk about rates, it's going to be surface gas or surface oil. Okay, these This is always a surface rate. Now, if we have gas, then we don't write QP, we write GP for gas. Okay? G for gas. Makes sense. If we have an oil, then we don't write OP. That would make sense, I guess. We write NP. I don't know why N. It's just the way it is. Okay? The volumetric material balance is basically something that can be used only in boundary dominated, if you've reached the boundary dominated time. Okay? Okay. So we're going to take the boundary dominated rate equation, and we're going to combine it eventually with this volumetric material balance, because we can do that because they're both valid in the boundary dominated period. And in this course, we're primarily only going to look at the gas, just to get the concepts down. Okay? Now, it's not going to be just a gas bottle, like a propane. It's not going to be just a gas bottle. We're going to take into account the fact that rock has compressibility, water has compressibility, and so forth. We'll look at a real gas reservoir material balance, but it's for this course, we'll just stick with the gas. Okay? So we'll take into account, obviously, the gas expansion, or whatever you want to call it, where this equation here is the all-important equation. But we'll also take into account water compressibility, rock compressibility, which we normally write formation, F for formation, compressibility. It's rock. Really, in reality, it's not rock, it's pore. It's how the pore volume changes. Formation, which is basically the same as rock, which is in reality what we want is the pore volume compressibility. Okay, that's what it really is. Pore compressibility. How does the pore volume change? Why don't we write it CP? I don't know. I just don't. Yeah.
In reality, I mean, we have another course that does material balance, and CF is actually fluid compressibility, and CR is the...
Okay, rock. Okay, so maybe use CR. But it's not rock and it's not formation. It's pore. Okay? So, just to confuse you guys. Okay. All right. So we're going to look at that. And then we're going to combine the rate equation. And since for this course we're going to stick pretty much with gas, gas rate as a function of PWF and P average, because it's the difference in the two that drives the gas. Okay? We don't have to use the average pressure, but that's what we usually do. So basically, this is the driving potential. This represents our pressure drop in Darcy's equation that pushes the gas from outer reservoir into the wellbore. We're going to combine this rate equation, reservoir rate equation, with the material balance. Well, since we're going to do gas, I'll just write GP. Why do we want to do this? Why do we want to do this? Whatever you like. Knowing how this looks into the future, this is what matters. This matters to your salary, it matters to your boss's salary, and it matters to your boss's boss's salary, okay? And all the stock owners of the company who own the company you're working for, okay? The value forecast is alpha omega. Here we are today, and we need to know what it's going to look like in the future, right? This is basically equal to the rate times the price, capital P. That's commodity price, dollars per barrel, dollars per MCF, whatever it is. Okay, it's just the sum, of course, over all the wells. The price of the gas, price of oil, dollars per 1,000 standard cubic feet for gas. That's ranging anywhere from today. I think I just heard from my friends in the States, they're whining, well, I understand they're whining. It's like $1.50, whereas in Europe it's about $6, $7, I think still. Okay, for gas. This is MCF per day. Okay. Okay. That's what we're looking for. Now the price forecast, somebody else is going to do. Okay, somebody smarter than us, because we don't know what the price is going to do. But somebody's going to put that number on that. But this is your job. That's your job. That's our job. Okay? And if you combine rate as a function of average pressure and drawdown, and then you've got another relationship that gives basically average pressure as a function of the integral of rate, then what do we have when we couple these together? It gives us then how rate can be expected to vary as a function of time. That's why we do it. The material balance is the integral of rate with time, and it doesn't care the profile at all. It just needs to know how much have I taken out. I'll tell you the average pressure. Then the Darcy equation, the rate equation, says if I know the average pressure, I can calculate the rate for any controlled drawdown, for any choke size. So we can work back and forth continuously to find the production rate profile versus time. And you can look at all kinds of scenarios, okay? Because the Germans, they may want for 5 years a certain amount of production, or they might want less production for 8 years. No, that can't be right. On the scale. Well, let's just say it doesn't time. Well, the Germans are not going to buy gas for 3 years. I mean, on a fixed contract. But the point is that you can start evaluating producing more gas or less gas for shorter or longer periods of time. And the material balance doesn't care what that profile looks like, okay? It gives the feedback. If you've taken so much gas out, you go back to this equation, you can say, well, at that point in time, I can produce this much from every well today, or tomorrow, or the next day. So that's the reason for doing this coupling. Okay. And we'll end up doing this just with a simple Excel spreadsheet solution. We use, I don't know, 1 month or 3 month time periods, and we say, well, I want to make the profile look a certain way. We'll combine these equations kind of in a very simple way in an Excel spreadsheet. And then you can actually, that's method 1. And method 2 is to do the coupling analytically, where you actually use your mathematical skills to kind of couple the two together analytically. And then you get what we call boundary-dominated decline curve analysis. Decline curve analysis. Okay? You get basically a simple equation. This boundary dominated, there's an equation by ARPS, and that ARPS equation is derived in many different ways by a guy Fetkovich we'll be talking a lot about here, the rest of the course. But this equation basically gives rate as a function of time. You take the initial rate when it goes on decline, that would be this rate or that rate. That's the initial rate when the well starts on decline. 1 plus a constant B times a constant D times time, 1 over B. And basically, you'll find that this will range from about 0 to 0.5 for conventional reservoirs, where you have one reservoir volume you're draining. You have a single material balance, okay? Okay, so this is for, you're basically draining a single, what I will call reservoir unit. Meaning that you can have a material balance of that single reservoir unit. Okay? If B is 0, okay, if B is 0, then this actually can't be solved because you got 1 over 0. But that actually analytically will just simply be that. Okay? And this is called an exponential decline. This is called a hyperbolic equation, a hyperbolic decline equation. And D is called the decline constant. or the rate of decline. Constant. And it can be shown to be equal to Qi over the ultimate at time infinity production. The final, you know, when rate goes to 0, you've got everything out. That's the ultimate or final cumulative production. And then you've got to have 1 over 1 minus b here. So as the rate goes to 0, you're getting nothing else out. You've produced everything you're going to produce. That's this term QP infinite. Okay?
Is that also a function of recovery factor, or?
Obviously, because that's all you're getting out. That's the ultimate recovery factor times the initial in place. Yeah. Recovery factor, this is just a term, times the initial fluid in place. It's recovery factor. And in this case, it's the ultimate or final. And the initial fluid in place is referred to as, well, generically Q, but that's initial gas in place is G, and N is initial oil in place. It goes with the NP. So that's the final ultimate recovery factor. And for gas, this is typically at minimum 50%, and it can go up to 98%. The first North Sea, not Norway, but the first North Sea gas field developed was called Hewitt in the UK. Phillips was one of the, maybe not the operator, but was one of the owners. I think Chevron was involved. That reservoir, it's been produced about 98% or more recovery. They basically put the well on, they sucked the well out with compressors. The permeability was so high that they got economic rates, you know, with only a couple of wells at the very end. I mean, they basically reduced the pressure almost down to nothing. North Sea offshore gas field. So if you have a high enough permeability and you don't have the ocean coming upon you, water moving in, then you can actually deplete almost everything from the reservoir, near 100% recovery. But typically it'll be 60, 70, 80%. For oil, it can be for example, the Bakken, which is the multi-billion barrel field. It's not shale, but it's just really tight rock in North Dakota, 5%. Up to, if you do nothing, you might, 50%. Of course, if you're in Norway, they say it's 60, 70%, but don't believe them completely. Okay. But it's a goal to reach 60, 70%. But I mean, this number is typically going to be 30, 35% at the best. Why? Because oil likes to stick to the rocks, okay? Oil and rocks are in love, okay? So the oil just wants to hang on to the rocks. Interfacial forces, okay? That's why. Gas, you can still, the gas can be coating the rocks, few molecules, but that few molecules coating the rock is, you know, represents nothing in terms of volume. The oil sticks to the rocks. Okay? So you have to work to bring the recovery factors above 30, 40%. You have to really invest a lot of money usually. So the value of B that you should use are given guidelines by a guy named Michael Fekovich. We'll talk quite a bit about in the rest of this course. But basically he just takes the rate equation, material balance equations, different forms for oil, different forms for gas, analytically solves them, and kind of shows what's the expected value of B for a given type of well. Okay. This is the start of decline. So this is the T equals 0 in ARPS. Okay, for example. Time 0 in ARPS is the day the well goes on decline. It's not the real day 0. It's when the well goes on decline.
Question. Isn't that related to how much rate you are constraining your well to? So for example, if you're producing, because here it's kind of fixed, right? So if you're producing at a higher rate, then this ARPS will be shorter.
I'm not quite sure. If you have a more or less constant rate, during this period here, what's happening to the bottom hole flowing pressure? Okay. Because the average pressure is getting less. You know, as you take stuff out, the average pressure always goes down. Okay? It's like death. It's the only thing you know is going to happen. So you take stuff out, the pressure is going to go down. So the driving potential for the rate equation, rate is equal to basically delta P, which is P average minus PWF, okay, times KH. Okay? So that means that the bottom hole flowing pressure also has to be decreasing. So the bottom hole flowing pressure during this period here is changing, as is the average reservoir pressure. Because the rate's constant, the delta P has to be constant. Which comes back to our definition of boundary definition. If I'm the guy at the well bore measuring pressure versus time, okay, and I'm getting 1 psi per day, and you're out in the, we're halfway out in the reservoir where you're getting an average pressure, it's also dropping at 1 psi per day. Because we have a constant rate, so the pressure is dropping at the same rate everywhere. Okay. Yeah. So that's okay. Now, if Professor Klepper was here, okay, which he's not, and he never will be, and never has been, but if he was here, he's the guy who teaches reservoir simulation, okay? And what would he say about this? Well, I've heard him make comments after Mike Fetkovich, who got his Doctor of Technology degree from NTH, on all the work he did from this university. I heard the comment, oh, well, that's all, simple play game stuff. Okay? Reservoir simulation is like, it gives you the right answer. Okay? So what is reservoir simulation? I'm just going to tell you what that is in a nutshell. You won't like it. Reservoir simulation is taking the reservoir and making it into a bunch of Lego blocks. You just basically discretize it into little Lego blocks. And then you set up an equation for transport from one Lego block to the next. And what equation do you think we use in the reservoir simulators to calculate what goes from one block to the next? Darcy. Oh, it's the same guy. Okay? And what do you think is the constraint on the differential equations, which they're solving? Okay? For every little grid cell. The material balance. Same deal. That's all they have. It's just that they have the same rate material balance equation for every little Lego block. Okay? So it's the same stuff going on. There's no advanced stuff going on, except that for one reservoir unit, as I said, we'll be solving here, it's like one Lego block. And what you're saying is that the whole reservoir can be treated as a single Lego block. Okay? Which is sometimes not a bad assumption. For example, the Hewitt field, okay, and there's a number of fields where you can make that simplifying assumption. And there's many, many other reservoirs where you can't make that assumption because you have multiple reservoir units or the properties vary so much spatially. There's many reasons why you need reservoir simulation. But don't get it wrong, you're basically using the same equations. Darcy's law and material balance. Okay? So hopefully when we go through all this, you'll actually be able to carry this with you into the mess of equations that Professor Klepp will throw at you on the wall, all the differential equations and the differencing formulations and forward differencing and backward differencing and central differencing and whatever else it is that makes everything appear confusing, but they're really just solving the same set of equations just a bunch more times.